In this video, we're going to talk more about normal distributions and how we can calculate probabilities for values that don't fall within exactly one standard deviation or two or three, like the empirical rule. So we're going to start with a little warm-up to remind us about z-scores. So we have an example here. You drive 65 miles per hour on a highway where the average speed is 70 miles per hour with a standard deviation of 10. I should say miles per hour. You drive 90 miles per hour on another highway where the average speed is 110 miles per hour with a standard deviation of 15. We want to know which highway are we driving faster. And the faster is in quote here because we know that 90 miles per hour is faster than 65. But if you were looking at cars traveling and you couldn't tell their absolute speed, you could just tell the relative speed to one another, in which group of traffic would I be driving faster, or would you be driving faster compared to the other cars around you, going 65 on this first highway or going 90 in this second? So let's start with Highway 1, just that first example. I'm going to find the z-score. So the z-score is going to be 65, which is the value, minus 70, which is the mean, divided by the standard deviation, which is 10. And so we get a z-score of negative 0.5. So if you saw my car, I would be driving slower than the people around me, but not much slower, just a little bit slower. On Highway 2, what would my z-score be? So I'm traveling 90, but the speed limit's not the limit, but the average speed is 110, and standard deviation is 50. So here I am more significantly below the average. I'm 1.33 standard deviations below the mean instead of just a half standard deviation below the mean. And so I would be driving in this scenario, I'd be driving considerably slower, than the cars around me. Whereas this one, I would only be driving slightly slower than the cars around me, which means I would be driving faster, in quotes, on Highway 1. Again, because it's the larger of the two standard z-scores. All right, so now let's look at an example of normal distributions. A test has an average of 70 with a standard deviation of 15. And the test scores were normally distributed. Find the probability you will score under 90. Okay? Now, if we looked at the normal curve for this distribution, 70 would be in the center of it, and we'd have 85, 100, 115 to the right for 3 standard deviations, and then we'd have 55, 30, and then 15 on the lower side. Sorry, I think I did that wrong. 55, 40, and then 25 on the lower side. And it would follow the empirical rule. However, 90 is not one of those values that's exactly one standard deviation away. So we have 85, and then we have 100 on the right. So 90 is in between. So we have this in Excel. We have this norm.dist function. We've already worked with this with z-scores, but we can use this for any distribution. It does not have to be the standard normal distribution. And notice how it finds the proportion of values, or the area under the curve, below a given value. So the norm.dist, if you put in your x value in this case it'd be 5. If you put in the mean, which was 3, and the standard deviation, which is 2, it would spit out, and of course we're putting true here, it would spit out the number 0.841. It would actually give me more decimal places than that, but rounded to 3 decimal places, it would spit out the number 0.841. And that's the area below that value that I plugged in, which was 5. So let's go back to this value, or to this problem. We have our x, we have our mu, and then we have sigma. I'm going to insert a sigma here. So this is the standard deviation. And in this case, we want to score under 90. So 90 would be the score I'm interested in. The average was 70, and the standard deviation was 15. So by default, the binom.dist function, the norm.dist function will find us the proportion or the probability underneath or less than this value. So what we're really looking for is the probability that x is less than 90. So the probability that x is less than 90, in this scenario, I'm going to find that by doing norm.dist. I'm going to plug in 90, comma, the mean, comma, the standard deviation, comma, true. And this will return 0.90878. And so in this case, the probability that you'll score when you take this test, that you'll score under a 90 is pretty high. It's a 90.87 or 88% chance that you're going to score below a 90. So how do we find the probability then that we score over a 90? Well, the total area under any normal curve is 1. So we have 0.841 here on this graph. This section right here would be the remaining 0.159 to give us 1. If we add those together, we'll get 1. And so in this case, if I already know the probability that you're going to score below a 90, the probability that you're going to score over 90 is going to be equal to 1 minus the probability that you scored less than a 90. And remember, we're not including the actual score of 90 in this scenario because in this scenario, the area under the curve under a single value doesn't change. It only changes as we accumulate area going down or up. So over a 90 would be 1 minus the probability of getting under a 90. Oops. So to find that, I'm just going to do 1 minus the value I got in the previous problem. And that gives me a 9.12% chance that I'm going to score over a 90. So again, the areas have to add up to give me 1. Below and above have to add up to give me 1, which kind of sounds like a binomial distribution, a binomial random variable. What we've essentially done in this case is we've found a success and a failure. In this case, depending on how you word it, the probability that you score under a 90 could be, under a 90 would be the success, whereas scoring over a 90 would be the failure. And notice how they add up to 1. So now, if 10,000 students took the test, how many would expect to score above a 90? Again, we just found out there is a 0.0912 chance that someone's going to score over a 90 on this test. So if we're looking for the expected value, okay, knowing that it's a 0.0912 chance that you're going to score above a 90, we can use the mean being equal to NP, where P, in this case, is our probability of success. And our probability of success is this number up here. We just found it. So in this case, the probability that I have a success, meaning scored above a 90, is 0.0912, or 9.12%. So if I wanted to find the expected value for 10,000 students taking the test, n becomes 10. So mu, I'm going to move this over. So mu becomes n, which is 10,000, times p, which is 0.092. And so we would expect about 912 out of the 10,000 students to score above a 90. Okay? But we'd like a range to go along with this. So we can also find the standard deviation. So remember that the standard deviation is equal to the square root of NPQ. So it's good, and I probably should have done this on the last one. We should have labeled our N, our P, our Q, and we know that N is 10,000. We know that P is this value here, and we know that Q is going to be 1 minus that value here, or the original value that we got up here. The probability that I don't score above a 90 is the probability that I score below a 90. So in this case, then sigma is going to equal the square root of n times p times q. And so we get 28.79. And so to answer this last question, if 1,100 students got out of the 10,000 got over a 90, would we be surprised? Well, let's find out what the normal range is. Remember, outside of 3 standard deviations is extremely rare, and it's going to make me take pause. So if I take the mean and subtract 3 standard deviations from it, and it helps to lock these references, because I'm just going to now copy this over and change the minus to a plus. We can see that we should expect the normal range to be about from 825 to 998 students. So if 1,100 students scored above a 90 on this, 1,100 out of 10,000 scored above a 90, I would be surprised. I would be very surprised. So this is our interval here of where we would expect values to fall in between. So yes, I would be surprised. Outside of 3 standard deviations is rare.